My invisible friends, hello and welcome back to our series on electrical engineering. Tonight, it is the third video on the sub-series dedicated to the op-amp. It's about its behavior, its model, and what is negative feedback. Very often at the beginning of this lecture, my students in the classroom want to know what is inside the op-amp. Now tonight it is about the behavior of the op-amp. Tonight, we want to know how it behaves and what we can do with that op-amp. And for that, we need a very special equivalent circuit, one that emphasizes its behavior. The op-amp is an amplifier, but it has not one but two inputs, VP and VN. It amplifies not VP, it doesn't amplify VN, it amplifies the difference, VP minus VN. The names of those input terminals are the inverting input and the non-inverting input. You may call them the N terminal or the P terminal, even the minus and the plus one. But please, in my classroom, never call them the negative or the positive one. The equivalent circuit has not one, but three input resistances. Three? Not two? How come? Let me show you. Here, those are the three input resistances. O1 between each one of the inputs and the reference node. This one, the R common mode, and there is an R differential mode that is between the two input terminals P and N. Those. The value of the R common mode is so much bigger, so much larger than the differential mode that we will simplify the circuit further into this one. Let me redraw the circuit for convenience. This equivalent circuit emphasizes that the behavior of the op-amp is described by three parameters. The input resistance Ri, the output resistance R0, and the open loop voltage gain A or AV0. Typical values for those three parameters are given by the textbook by Alexander and Sadiko. The input resistance can have a value between 100,000 and 10 teraohms, that is 10,000 billions of ohms, a pretty large number. The output resistance, in comparison, is insignificant, between 10 and 100 ohms. The open loop voltage gain is a fairly large number too, between 100,000 and 100 million. The ideal op-amp can be characterized by an infinite input resistance, a null output resistance, and an infinite open loop voltage gain. In this course, and only for this lecture, I will keep A as a large but non-infinite number, a finite number, A. And then after I show the circuit, all the voltages will come out as functions of A, and I let A tend to infinity to see what happens with voltages in the nodes of the circuit. This is the equivalent circuit for the ideal op-amp that we will use. An infinite input resistance, zero output resistance, but a finite value for A that will tend to infinity. The input currents to the ideal op-amp are zero. Now we must talk about saturation and the op-amp. Do you remember that the output of an amplifier is bound by the voltages of the power supply, cannot exceed the top rail or go under the bottom rail, or it saturates? The reality is that those rails are not exactly at plus VCC and negative VCC. The top rail is at VCC minus delta, and the bottom rail is at negative VCC plus delta. The value of delta depends on how expensive the op-amp that you're using is. For a very expensive high-end, the so-called rail-to-rail op-amp, delta can be as little as 0.1 volts. But don't be surprised that for less expensive op-amps, delta is as large as 3 volts. The point is that no matter where the top and the bottom rails are, the output of the op-amp cannot go above the top or below the bottom rail. If it tries, it will just get stuck at the rail and the op-amp will be saturated. Because the op-amp has such a huge voltage gain, even the smallest difference between VP and VN will get it saturated. But if we take just a little bit of the output and we feed it back into the inverting input, we just may keep the op-amp from saturating. How we do that? We connect either one or more passive elements between the output and the inverting input. I better show you, right? Here, this is a passive element and it's connecting the output to the inverting input. That op-amp has negative feedback. What is the effect of negative feedback in the amplifier then? We better analyze a circuit with an ideal op-amp, but that has a non-infinite open loop gain A And then we see what happens when we let A tend to infinity. We identify the nodes N and P, choose the directions for the branch currents, and say, in that circuit, there are two true nodes apart from the reference ones, N and O. But O is connected to the reference through a voltage source, so its voltage can be written right away as V0 is A times Vp minus V and the value of the voltage source. For the other node, we will write a KCL equation. Currents going in equals to currents coming out. Going in, Vi minus Vn over R1, the current from the left, equals to 0. 0 who? The zero entry, the inverting input of the op-amp, plus the current on the top, Vn minus V0 over R2. If we substitute V0 in the first equation and write it over here, we can solve for Vn. Vn, that is Vn. If now we let A tend to infinity, this term on the numerator becomes irrelevant, and so do R1 and R2. And the limit, Vn tends to Vp. Let's say that in words. When A tends to infinity, Vn tends to Vp, and the limit, Vn will be equal to Vp. That is the point. With negative feedback in this op-amp, with an infinite open loop voltage gain, Vn is equal to Vp even though they are not connected. This is the most important conclusion of op-amp so far. If the op-amp is not saturated and has negative feedback, even though P and N are not connected to one another, they have the same voltage. It's an extremely important conclusion, the one that will simplify our lives for the rest of the course. You don't trust my math? Let's use the HP prime instead. There is your KCL equation, solve for Vn, and find the limit of Vn as A tends to infinity. And what is it? Vp. Same as before. If A tends to infinity and there is negative feedback and the op-amp is not saturated, Vp is equal to Vn. Negative feedback, no saturation, Vn is equal to Vp. That is the most important equation we've found so far. So important that we will add it to the M&A method of solution of circuits. So far in M&A, we defined three types of equations. KCL for every true node, a KVL equation for every evil branch, and a CTL equation for every controlling variable. Tonight, we're introducing op-amp circuits only, a fourth type of equations, the NF type. What equation is that? You guessed. Vn is equal to Vp. At the very beginning of an op-amp question, where I'm using ideal op-amps to solve the circuit, I ask myself, this op-amp doesn't have negative feedback, and if it does, I write right away the NF equation. Vn is equal to Vp. Let's work on some numerical exercises. On the circuit below, all resistors have the same value, 100 ohms. The voltage source on the left is a 10 volts voltage source, and the op-amp is an ideal op-amp with an infinite open loop voltage gain. Let me copy it here. Identify the nodes 1, 2, 3, 4, 5, and 6. Choose the branch currents arbitrarily as always, and we ask ourselves, is there a negative feedback? Here there is negative feedback because the output, node 6, is connected to the inverting input, node 3, through those three resistors, RFA, RFB, and RFC. There is negative feedback, so I write right away the NF equation, NF, which is Vp is equal to Vn. In other words, V3 is equal to V4. First equation. Now we write equations for the nodes. You say, do I write an equation for this node 6, a KCL equation? Only if you need the current I0 that comes out of the op-amp. If you are computing I0, yes, I recommend that you write a KCL equation for node 6, but if you're not, which is my case right now, I do not write that. I don't need that current. I don't write an equation for node 6, a KCL equation for node 6, I don't. But I write then a KCL equation for node 1 on the left, node 2, node 3, node 4, and node 5. I invite you to freeze the video and check the validity of my equations. We have 6 equations and 6 unknowns, V1, V2, V3, V4, V5, and V6. We enter them in the HP prime CAS system and solve for them, and those are the solutions. V6, the output of the circuit V6 is negative 2 volts. Another one, but this one a little bit harder. Let's solve this circuit the hard way with no knowledge or use of the negative feedback concept, because in this circuit I am not so sure there is negative feedback. The op-amp on the right has negative feedback. That is evident. That 3 kilo ohm resistor is connecting its output to the inverting input. But what about the op-amp on the left? If you're thinking that that 12 kilo ohm, this 3 kilo ohm resistor, and the R resistor are connecting the output of the A op-amp to the inverting input, think again, because you see this combination of 2 resistors and 1 amp is an active element, an active component, so I am not so comfortable just saying, yes, the op-amp on the left has negative feedback. No, I will not make such an assumption and just use electric circuit theory to solve that. This will be the model that I'll use for the op-amps. Infinite input resistance, zero output resistance, and a finite value for the voltage gain A. There is no current at the input, and the output voltage is given by the value of the source, A times Vp minus Vn. Identify the nodes, choose the branch currents, and start. We write an evil equation for node 5. V5 is A times Vp minus Vn. Vp is 5 volts, and Vn is V1. And for the second one, the same thing, evil equation for node 6. V6 is A times Vp minus Vn. In this case, Vp is 0, and Vn is V3. We write a KCL equation for node 1, KCL equation for node 3. We enter them in the calculator and solve. And of course, the voltages will come out as functions of AV0, of the open loop voltage gain. If we find the limit as that gain tends to infinity, we find the actual value of that voltage for V1, V2, V3, V4, V5, and V6. Those are the values. Don't write them like that in my exam. Please use floating point numbers this way. That is much better. That is the solution. V1 is 5 volts, same as V2, so after all, there was negative feedback for the op-amp A. I just didn't know. If we had known that there was negative feedback, we could have written for the op-amp on the left that Vn is equal to Vp. V1 is equal to V2 is equal to 5 volts. And for the second one, negative feedback. Vn is equal to Vp, V3 is equal to V4 is equal to 0. And we write, of course, KCL equations for nodes 1 and node 3. What about node 2? Node 2 voltage is known as 5 volts. Or node 4, V4 is 0. V6, we write KCL for V6 only if I care for the output current of that op-amp. The same about V5. Now, KCL here and KCL there. That is all I need. Enter them in the calculator, solve, and we get the same solution as we got before, but with much less pain. No limits here, but only if we know in advance that there is indeed a negative feedback. Suggested homework. Solve the same circuit, but not with 2 ideal op-amps, but with 2 real op-amps that have these parameters. Input resistance, 200 kilo ohms, output resistance, 70 ohms, and open loop voltage gain, 300,000. Good luck with that. An important note, what to do if R0 is not negligible, is not 0. If the op-amp is ideal, this is a situation that we visualize in our minds, and we write a KVL, an evil equation for node M, and we say Vm is the value of the source, A times Vp minus Vn. But if R0 is not negligible, as sometimes it isn't, this is the situation that we visualize, and we don't write a KVL, an evil equation anymore. We write a KCL equation for the output node of the op-amp, which is currents going in on the top, Va minus Vm divided by Ra from the op-amp, Avx minus Vy minus Vm divided by R0, and currents leaving the node, Vm minus Vp divided by Rb. Remember, if the output resistance of the op-amp is not negligible, is not 0, then we don't write an evil equation for the output node, but we write a KCL equation instead. This is particularly important because real op-amps, which have almost ideal input and gain characteristics, they still have an output resistance that cannot be ignored all the time. To complete this lecture, I have to talk about offset balance. Balance of what? This is the case of a T L081, one of my favorite op amps. We identify what the pins are and see that it's not connected to anything. The power supply is connected between pin 7 and pin 4. The inputs are pin 2 and pin 3, and the output is pin 6. What are the other two? And here's the situation. If the op-amp was perfect, whenever I short circuit pins 2 and 3, Vp minus Vn is 0, the output V0 should have been 0. But in reality, it hardly ever is. So this is what we do. According to the manufacturer, who recommends fixing it this way. We short 2 and 3. We monitor V0. It's not 0. It should be 0. And then between pins 1 and 5, we connect a small potentiometer, 100 kilo ohms, small potentiometer, like so, between pins 1 and 5, and the cursor of the potentiometer through a 1.5 kilo ohm resistor we connect to the negative of the power supply. We slide the cursor, monitoring V0 until V0 is 0. When V0 is 0, we glue in place that potentiometer, we remove the short between 3 and 2, and we use the op-amp. It has been balanced. Summary: if an op-amp has negative feedback and it's not saturated, Vp is equal to. There is one final exercise that some of you have asked me to include in this video. This one. In that one, on the top op-amp, I am not sure there is negative feedback. Identify the nodes, choose your branch currents directions, and write your equations. Evil equation for node 3, evil equation for node 5, case equations for nodes 1, 2, and 4. Enter them in the calculator, solve. The solutions come out as functions of the open loop voltage gain of the amplifiers AV0. Find the limit as AV0 tends to infinity, and those are the values of the solutions. Those are the voltages. In particular, the output V0 is V3 is 2 volts. And that is all, my friends. Thank you very much. But before I say goodnight, I invite you to watch 2 more videos in this series, in this playlist. One of them is the final tutorial on op-amps that has been on this playlist for years. It's very successful. Students really like it. And the other one is a new one that I will be publishing soon. The 8 op-amp circuits that changed the world. And with that, I sign off. Have a great night. Thank you very much.